So we also have this example. This example we did was just a straight system, but the system yielded some eigenvalues. Let me write those eigenvalues down. I can see them in the solution. I could also recall them, and the eigenvalues were -1 plus or minus the square root of 11i. Okay? There are two things that are going on here. The first thing is the imaginary part causes a center like dynamic. Okay? So we're picking up this imaginary part, and that imaginary part we're going to color code in purple. That's the imaginary part, and it causes, just as before, something like a center to happen. Okay? Now, there is also this real part right here, which I'll code in orange. Well, first, before I get done or do the real part, notice that that imaginary part appears right here. The imaginary part, which is causing a center-like dynamic, is only associated with the sinusoids in the solution representation. Okay? There is this other component, which is real. That is the real part. And that real part we'll list in orange. And that real part causes a growth or decay. So where's this real part? This real part is appearing in these exponentials, and so here my real part is negative. So if the purple imaginary part is causing the swirling, the real part in orange is causing that swirl to either go into the origin or out from the origin. Okay? And so what we get here is a sink behavior. So we get a sink at 0, 0. Why do I get a sink at 0, 0? Well, that's because as t goes to infinity, all of these exponentials are going to decay. And if all of these exponentials decay, all my styrofoam peanuts are going to 0. So I get a sink, but this happens to be a complex eigenvalue. So I would call this a spiral sink. Or some people call it a complex sink. Regardless, the sinking is because of the -1 real part. And the spiraling, or the complex, is caused by this imaginary component right here. So, here's the issue. We were able to draw such nice diagrams before because of the straight line solutions, which we don't have anymore. Okay? So, I know that I'm going to start a particle off in the space, and then that particle is going to move, and so it could spiral into the origin, or I mean it will spiral into the origin, but it could go this way, or it could go this way. So I know spiral, I know into the origin, I just don't know clockwise versus counterclockwise. So, to figure out if we go into 0, 0 clockwise versus counterclockwise, so those are abbreviations often used for clockwise and counterclockwise, we can test the field. What do I mean by that? Well, remember, these differential equations are defining vector fields, and the solutions are curves, which the styrofoam peanuts trace out as they move dynamically through the space. Right? And so, to get an idea of clockwise versus counterclockwise, I can just test out what's going down. What would I test? I could test this point right here, which is at 1, 0. And so I can do A times the vector x, which is my A matrix, -3, -5, 3 and 1 times my proposed x vector. And let me just erase that x vector and just put I hat. That's totally what we're using, so I'll just put I hat right there. And now I perform the multiplication. I do negative 3 times 1, which is negative 3, minus 5 times 0, so I get a negative 3. And then I do a 3 times 1 plus a 1 times 0, so I get a 3. And so if this spot right here is my point that I'm going to release the styrofoam peanut, what does this vector mean? Well, this vector is the derivative of the curve at that point, which would be the tangent to the curve in the plane at that point, which tells me at that point, should I be going left or right? I should be going left, and should I be going up or down? So I should do something like that. I should go to the left and up, right? The left is the negative 3, the up is the 3. And so what would my solution do? At that point, I drop the styrofoam peanut in, and then I flow up and to the right, but I know down deep at the end of the day, where do I gotta go? I gotta go to the origin. And so I just draw some spirally curve going into the origin. I don't know how tight the spirals are. I don't know the alignment, whether or not an ellipse is formed and in what direction of the ellipse. All I can tell you is that I will go to the origin, I will spiral as I do so, and I will go counterclockwise. So here, I can't get nearly the details that I did for the real eigenvalue case because I don't have any straight lines. And then the bulk of mathematics needed to deduce whether or what ellipse I have and the positioning of the ellipse, it's definitely not in the cards. It's not worth the effort. At least not for our needs. And I've never had to really dig that deep. But I think if I had to, I could do it. I'd like cash money for it, though. Okay, so what I'm going to do is I'll fade away. You can take any last notes from here, and let's get the computer visualizing exactly what this is, or what this looks like. Okay. Strange question. Oh yeah, I should label this thing. Okay, and then I'll get back to the question. What is this thing? This thing is the red thing, and I would say that 0, 0 is a stable spiral sink. So, let's see. If I could color code this, what I would tell you is that if this is my eigenvalue being complex, that's what I'm associating with the spiral. The stability is brought up by the real part being negative 1. Okay. Camera 4. Yeah, totally. There is an ellipse under there, but when I come back through to the point that I was at, because of the decaying exponential, I'm a little closer to the origin. So there is kind of an indicative ellipse shape that's been turned and elongated here, but I don't ever make the ellipse. The styrofoam peanuts don't make it all the way back around to the point they were at. Because of the decaying exponential, as they go on that elliptical trajectory, they get closer to the origin on every pass, and actually in this case faster, right? Because I don't even make it to the backside before I start spiraling in.